Good afternoon, everyone, and a warm welcome to all of you who are joining us today for our 2024 open house for the Van der Schaar Lab. I'm delighted to have you all with us, sponsors and collaborators. We are very excited to be telling you about how we have been pushing the boundaries of what is possible with machine learning in the past year, and how we are advancing our reality-centric agenda. You, of course, know me, Mihaela van der Schaar, and you know quite a lot of the PhD students in our lab. You see all of them here. Some of them may be familiar faces, but we also have a lot of new PhD students in the lab. We have 5 students that have joined us this year: Antona, Claudio, Harry, Thomas, and Victor. We are delighted to welcome them, and they are going to be presenting their work in future open houses. We are a truly international lab, and last year I was presenting this world map, with all the various countries that our students have come from over the years. And at the time there were 18 countries. Now there are 19 countries that we have had students over the past 20 plus years since our lab has been in existence. And I hope that all these gray areas are going to be providing a wonderful PhD student to our lab in the near future. Also, I would like to say that very much part of our lab is my key collaborator, Andrew Rashbas, who is the former CEO of The Economist, Reuters, and Euromoney, and a professor at Harvard Business School. Andrew has joined us a few years back and has been an integral and important member of our group. And it is really a few years back, around 2 years now, that we have put forward the case for reality-centric AI. Most of you know by now what I mean by that, but I would like still to highlight this theme of our lab. We believe that we really need a fundamentally different paradigm for AI than it is currently in use today, to orient it towards addressing the complexities of the real world. We have seen this year 2 Nobel Prizes in physics and chemistry, and definitely AI is making a big advance in science. But there are many other areas in which AI really could play an important and pivotal role, and it is not. Whether it's changing healthcare, changing medicine, changing the way we educate and teach from a very young age to continuous learning through adulthood. We still have not built AI that can prevent a climate catastrophe or deal with the traffic in cities like London, where I live. So it is really important to move from the current way in which of a lot of AI at the cutting edge is happening, where we take a fixed data set and we apply machine learning to it, or we have very toyish benchmarks that involve mazes or very stylized simulations of the real world. We really need to engage with the complexity of the world. And it is this reason why we have defined this reality-centric AI agenda. If you are not familiar with our manifesto, it is prominently displayed on our website, and you have here the QR code, and I invite you to take a look. Very briefly, reality-centric AI aims to solve big, complex real-world problems. It aims also to build AI which operates effectively and accountably, given the inherent and unavoidable complexities of the real world. And it is an AI that aims to put humans and humanity at the forefront, to empower them rather than marginalize or replace them. And we have outlined 8 research pillars that will bring us towards this reality-centric agenda. And today, 3 of them are going to be highlighted quite a lot in our presentations. Pillar number 2, where we are going to discuss about models which need to be designed to operate with messy real-world data. Number 5, models need to respond to dynamic measures of success. And number 7, models must be designed to consider when and how to communicate with humans. So after this brief introduction from me, we are going to have a first session where we are going to describe the next frontiers in AI for science, from pharmacology to physiology to physics and economics. Sam is going to kickstart this open house with describing some very new work we have done, where we are trying to discover pharmacological models from data. And it is very exciting because Sam was able to discover, using machine learning, a very powerful new pharmacokinetic model for warfarin, which is a very important drug. Then Krzysztof is going to talk about a very complex problem and one that has puzzled me for at least 10 years. I often give talks in which I say time is the new frontier for machine learning. And we have built a lot of machine learning over the years for the time series forecasting. But all the machine learning models that we have for time series forecasting, whether it's statistics, econometrics, or machine learning, are all black boxes. And Krzysztof, for the first time, was able to build technology that is going to present to you that goes towards being able to forecast and make forecasts from time series data in a completely interpretable way. And this is something very interesting and impactful because it's not possible today, was not possible in no other field, and will also enable us to make new discoveries and understanding. Then in a second section, we are going to talk about how can we make AI and machine learning work in the real world. And we are going to continue the journey with Nabeel that has been very much a pioneer in data-centric AI, and he continues to really lead this and define this research agenda. And among the many things he was going to tell you today is something, again, I'm very excited about, because we are going to be telling you how can we make how can we take data that is very small sample, like in rare diseases, or in many other discovery settings where we do not have a lot of data? And how can we take this very limited data and turn it into a much more rich and diverse set of data? How can we enrich all of that? Then Sam is going to return and he's going to tell you about something else that we are excited about, the world's first large language model-based automatic computer that is going to be able to generate extensive code. And what's interesting about this code is that this is not just hallucinating code. This is a code that has checks in it and validation. But other things that Sam is going to tell you that he can do with all this are, for instance, Italian recipes. We invent a lot of new Italian recipes with this method. So stay tuned. In the third session, we are going to tell you about digital twins. And this has been a technology that quite a lot of people talk about. But the reality is that really it requires a new transformation and a new way of thinking if it is to make this technology of digital twins useful for predicting disease progression, for being able to intervene early and be able to do early diagnosis, to be able to plan treatment strategies or improve clinical trials. So Tennison is going to tell you about some very new advances we have made in this area and how are we shaping the agenda on building digital twins that are able to deal with unique issues such as learning from a very limited sample size, generalization to unseen state action pairs to be able to plan treatments, or for that matter, evolvability over time to really unravel and think about what are possible futures for this particular entity, a patient, or why not, a hospital or a city. And we are going to end with a theme that is very dear to my heart, AI for human empowerment. Kasia is going to be telling you about a very new way of thinking about meta-learning. We call it informed meta-learning. And this enables us really to go one step further towards automated knowledge integration from human interpretable representations, thereby being able to build a dialogue between the knowledge that we humans have and the computers have. So we are teaching computers about our own knowledge in the hope that they are going to become more powerful and teach us new knowledge. Hao is then going to tell you about how reinforcement learning and inverse reinforcement learning, two technologies that we work on for many, many years, 20 plus years, how these techniques can be innovatively used to better do large language model prompting, fine-tuning, and inference time optimization. So if you think the large language models can do a lot, stay tuned, you'll hear a lot more. And we're going to finish this agenda today with Tim Schubert, who is MD PhD. He is a clinician in training who is affiliated with our lab and has been so for more than a year. And with him, we are going to show to you something else that we are very excited about. So for all of you in the audience who cannot write Python, who cannot do machine learning coding, we are going to show to you that you don't need anymore to do code. You don't need to be able to speak Python and speak machine learning language to be able to interact with machine learning and be able to build your own machine learning analytics. So this gives you an agenda, but our work is much broader than what you see today. We have had quite a lot of success this year again with publications and ICML at all the top machine learning conferences, from ICML to NeoRIPS to iClear. And I hope you are going to take a look to our website to learn more. Also, since our focus is not only on building cutting-edge ML, but also in connecting and impacting the real world, we have enhanced our interactions with a variety of other researchers and industry to make true impact in a variety of areas. And one that I highlight here that has been especially very wonderful for us was the collaboration with pharmacologists, whether it's in industry or in academia. But please take a look. And you see here one of our key collaborators, Richard Peck, talking to my former PhD student, Alicia Kurt, about one of the work that we have done recently on really trying to rethink the way we are using causal effect inference and causality for the sake of pharmacology. And quite a few other examples, ranging from using AI for knee osteoarthritis to building synthetic data for the entire UK Biobank. Also, we have developed a lot of new software and enhanced existing software, from risk prediction models to synthetic data. SynCity is especially a very popular engine that we have shared with the world last year and is growing, but also new suites for data-centric AI, data gnosis, and many others. Please take a look at our website for the software that we have developed. And please keep an eye in the next 2 weeks for the big release of Climb together with Evgeny and team, which is this AI-enabled partner that will enable you to really converse with machine learning without the need to code. And more about that by Tim later. Also, we have given a lot of tutorials over the past years at major conferences to disseminate our research and to build community by really providing our know-how at these large conferences to both shape the world and also tell the world our vision about the areas of research that we operate in. And one area that I really would like to highlight, and I'm really delighted to have such amazing PhD students like Nabeel Seedat, who is now in his final year, with whom I made really a major partnership to give a series of tutorials at really key conferences like our flagship conference, NeoRIPS, last year, and then more recently at IJCAI and MICAI. All these tutorials, or most of these tutorials, are available online. So even if you have missed them, you can take a look at our website and find them. Also, you can remain engaged with us through our inspiration exchanges, which are our monthly sessions where we are engaging with researchers from all over the world interested in cutting-edge machine learning, especially applied to medicine. And we hope that you are already part of these sessions and receiving our monthly emails and joining us monthly. But if you are not, please subscribe to them such that you are part of them. And I want to tell you that we are very excited that the next one is on November 4th, and we are going to talk about digital twins from a machine learning perspective. We also have a sister session called Revolutionizing Healthcare, which is aimed at clinicians. So if you are a clinician in the room, please join us for these sessions. We have by now 800 plus, almost 900 clinicians joining these sessions, which are actually co-hosted with Tim Schubert and Tim Osterling, two young clinicians in training who are to help me really shape up this agenda. And we are going to have a session on November 5th on digital twins, but this time more from a clinical perspective. So I hope you will join us. Again, all these sessions for Inspiration Exchange and Revolutionizing Healthcare are on our YouTube channel. We also have a wonderful symbiosis with CCM, which is the center that I lead, and which is actually a wonderful symbiosis because CCM has numerous researchers from other disciplines, amazing clinicians, but also biostatisticians, population health scientists, and many others, and ethicists, and many others. And we really have this wonderful symbiosis where a lot of our tools are driven by ideas that originate, for instance, in medicine, and vice versa. We bring tools to the center. And I'm very delighted together with Andres Flotto to really grow this center, CCM. And this past year, it has grown further. And we have new sponsors and new partners. Finally, I'd like to say big thank you to our machine learning engineers, communications, and Mihaela, who is our CCM center coordinator. So, and you received a lot of emails from her about this day to day. So I'm very grateful to all four of them. But what I would like to finalize this talk with is a big thank you to you, the sponsors, the numerous sponsors of our lab. We are extremely grateful to you for your confidence, for your support, for sparking so many wonderful challenges and ideas in us, and for collaborating with us so wonderfully. We are extremely grateful to you. And we really hope that you will continue to engage with us such that we can together co-develop this agenda and deliver the promise of machine learning to create major real-world impact in a variety of fields to benefit society and humanity. So we hope that you are part of this agenda to solve these biggest challenges and transform the world for the better. With this, I would like to stop sharing screen, and I would like to give the floor to Nabeel Seedat, PhD student in my lab, a wonderful collaborator, who is going to chair our agenda today. Thank you, Nabeel.
Hi, good afternoon, everyone, and welcome to the Vandasha Labs Open House for 2024. So I'll be chairing today's session. So just a bit of housekeeping before we get into it. So as Mihaela mentioned, we have about 8 presentations across the 3 to 4 thematic areas. So each will be around 15 minutes in length. And without further ado, Sam to kick off Next Frontiers in AI for Science.
Great. I'm excited. Let me start. Great. Yeah, so to kick off some of the frontiers, so in the next 10 minutes, 15 minutes, I'll be covering one of our latest papers that we just got accepted in Europe, which is data-driven discovery of dynamical systems in pharmacology using large language models. And this is joint work by excellent co-authors Jiajie Gren, Tennison Liu, Jin Weatherhall, and my supervisor, Mihaela Venetia. So let's take a brief pause and actually let's focus on what is scientific discovery and why is it useful. And really, scientific discovery is fundamental to the scientific process. And actually, this goes back all the way to in the 17th century, Johannes Kepler was actually observing data sets of the elliptical orbits of Mars and actually hypothesized correctly a better fitting equation to such a data set, in this case, deriving Kepler's laws, as you can see in the bottom right-hand corner. Now, this process took Kepler 9 years of painstaking analyzing data and fitting curves and trajectories. But with modern machine learning methods these days, we can actually automate this process to discover, as you will, scientific laws or equations within minutes to hours, which is very exciting. So what we see here in the top left is a typical machine learning data set of data happening over time. And then we have some sort of output. And we're really trying to discover some sort of closed form mathematical equation. Now, really the inherent benefits of doing this is if we discover an underlying equation, we can actually represent the underlying process very accurately, and it generalizes very well to new data distributions. And we can also often discover such an equation with low amount of samples of the actual observation or phenomena that we're trying to discover. And this is really fundamental to applications like physics, pharmacology, and other sciences. But really, this actually compounds with particular problems where actually doing this is an NP-hard problem, which means it grows super exponentially with the amount of components within such an equation, such as discrete or continuous floating point components in an equation. Now, this has actually been a focus of the lab for quite many years, just over 5 years. And actually, we originally had work on this actually focusing on the scientific discovery for pharmacology. And I highlight actually a particular blog post here I encourage you all to read. And again, yeah, back in 2020, we focused on individualized modeling of discovering these equations and precision dosing. And it's really applicable to such real-world applications. But if we look at some of the work that we as a lab have actually done in this space, really we look at actually different levels of discovering some sort of underlying law or representation. So we can discover a explicit equation, in this case, some sort of equation, and this is really applicable for disease trajectory modeling of time or risk metrics over time. And we have a paper on discovering transparent time series models in ICLR 2024, as Krzysztof will mention later. We also have discovering ODEs such as decode and ICLR as well, 2 years earlier. And this really focuses on actually discovering differential equations such as tumor growth models, pharmacological models, or epidemiological models of diseases such as COVID-19. We can go further and actually discover partial differential equations as well, such as D-cipher. And we can even go further still with discovering general purpose equations with deep generative symbolic regression, what combined in ICLR as well. And really broadly, all these applicable, especially focusing on PDs, we can actually discover then spatiotemporal physiological systems and population models, particularly age-structured epidemiological models. So where is this useful? So this is useful for physics, medicine, and economics, and really real-world application of discovering some sort of underlying representation of the true process, what's happening underneath. So let's go into actually data-driven discovery and with large language models, this newest paper which we're discussing. So how can we actually discover the true underlying pharmacological processes that evolve over time? Again, as just pointed out, it's a very difficult problem. And really we want an importance on accurate modeling. So we really want doing this allows us to crucially understand the disease-drug interactions. We can optimize precision dosing, and we can also minimize adverse health effects. For example, a chemotherapy example, we want precise dosing, maximizing cancer cell eradication while minimizing patient harm. Now, this comes with the limitations of current models, such as high cost, lack of scalability, and also restricted human knowledge. In this case, existing models for pharmacology are often done by human experts, or pharmacological experts. So can we automate this process with modern machine learning methods? And the answer is yes. So we present such a solution to leverage large language models to iteratively discover and refine pharmacological dynamics models, or as we pose it, data-driven discovery, a D3 framework. Now, this provides us the inherent capabilities of proposing and acquiring and integrating new features. We can validate and compare pharmacological dynamic systems models, and we can uncover new insights into pharmacokinetic processes. And in demonstration, we demonstrated identifying well-fitting interpretive models across diverse pharmacokinetic datasets. So how does this work? So a user will come along with a real-world data set of some sort of physiological process, such as, in this case, maybe lung cell cancer, and actually the effects with a particular chemotherapy drug, and also come along with a description of that problem, and also the feature variables of this data set. Now, in the LLM, we propose a LLM agentic framework, which can actually understand this textual prior and generate, in this case, a interpretable mathematical model in the form representation of code. We can then automatically, within the LLM framework, take this code representation and test it on a validation loss data split of the data set, determine the model fit or the best fit. Now, with this, furthermore, actually, rather than just doing standard neural architecture search with such an LLM, we can actually ask the LLM to do feature acquisition as well, using the value information framework to then propose features that it believes that will be more indicative to improve a better model. And this is based on biologically plausible, realistic other pharmacological models or dynamics models we're trying to model. In this case, the LLM responds with, it would like to actually acquire particular features, in this case, radiotherapy dosage, and it can actually quantify a predicted improvement of the performance of that. Depending on the cost or the budget of the user, you could then go ahead and actually collect an additional feature for that data set and add it to that data set. Now, this then iterates in an iterative process. And most importantly, when the LLM goes again, we can actually see the previous, essentially, dynamics models generated by the LLM. And these are iteratively given to the LLM, and most importantly, can then reflect on creating more biologically plausible models for a generation. And then can actually use this reflection to then generate a better fitting model. And what we see is we can generate a better model over time gradually, and also acquire additional new features if we have a feature budget to acquire new features for. Now, this goes on iteratively for about 20 iterations. It's up to the user to specify that. And what we end up with is a very accurately fitting white box interpretable model, fully interpretable mathematical model, as you can see an example here on the right, with also some initial parameters that fit the population of patients that we have the data set for. So what we did with this, we actually leveraged it to a publicly available randomized controlled trial data set on a warfarin modeling data set. And what we were able to do was actually discover a new plausible pharmacokinetic model for the model. And baselining against the existing models that we could come up with the literature, we were able to achieve a significantly better fit in terms of held out mean squared error prediction on a validation data set of patients. Now, this really highlights its precision for using such a method to automatically discover some sort of closed form expression or equation. And doing this actually over different problems. So we looked at lung cancer data set, lung cancer with chemotherapy, and also lung cancer with chemotherapy, radiotherapy, a biologically plausible data set of biological species modeling, in this case, plankton microcosm, a COVID-19 epidemiological data set, and also this warfarin randomized controlled trial data set as well. And what we see if we compare it with existing machine learning modeling approaches, such as discovering equations through a sparse progression paradigm, such as SIMD, or such as Dynode, or even just using an LLM to, in this case, zero shot predict a code model based on the description, or actually code model and then optimizing parameters as zero shot optim, or recurrent record transformer, we can see we can actually identify well-fitting white box models. But most importantly, we can go a step beyond. We can also augment and ask the LLM to generate a neural network residual components within such a white box modeling framework to allow to actually take up the residual slack to then create a better fitting model that actually gets a better test mean squared error performance, as we can see with this hybrid approach in the bottom row. But most importantly, we're interested to take this to real world problems, not just synthetic problems. So here we've done this to the real world data set. And what we see is we can actually discover a better white box model. In this case, having a lower mean squared error than the existing warfarin PKD model. And this is the model presented on the screen. And this has some really interesting, nice new aspects or phenomena that actually fits the data better. And we'll go into those. And this is also biologically plausible, which is very, very promising. So we have Professor Ian McKinney, clinician, who she mentioned the model is significant, and entire consortiums are dedicated to improving such warfarin models. And this model actually adds novel components, such as the microbus component for time-varying changes and novel interaction terms like agent sex. We also had an expert pharmacologist, Jean-Baptiste Willard, who mentioned the model is promising and pharmacokinetically plausible, and the next step is to apply D3 to other clinically relevant PK drug datasets. So Richard Peck, an excellent clinical pharmacologist, and this model is also reasonable and potentially superior and represents a significant advance in clinical pharmacology. And really, we can automatically just identify robust QP models. And this is really just a start. And really, this is the initial proposal and proof of concept, but actually applying such a method to this to then apply it to real world problems is very exciting. So to conclude, and the contributions of this is we introduced the data-driven discovery framework, which leverages large language models to iteratively discover and refine interpretable dynamics models with an application to pharmacokinetic modeling and beyond. D3 addresses the difficulty in recovering interpretable dynamical systems by utilizing LLMs to explore vast model spaces, integrate unstructured data, and generate models with few parameters that match the accuracy of black box neural networks. D3 demonstrates success across pharmacology, epidemiology, and ecology, achieving accuracy comparable to the existing methods while significantly enhancing the model interpretability. A novel and more accurate pharmacokinetic model for warfarin was discovered using D3 and validated by expert pharmacometricians. And D3 iteratively refines its models, selectively acquiring features, and discovers precise dynamical system models, offering insights into models and feature selection. Thank you so much. And at this point, I'll hand back to Nabeel and Krzysztof.
Awesome.
And also, I'd like to thank the excellent sponsor, AstraZeneca, for making this work possible.
Hello everyone, my name is Krzysztof, and today I'd like to present a paper that we have recently published at iClear 2024, titled Toward Transparent Time Series Forecasting, authored by me, Tennison Liu, and Mihaela van der Schaar. So first, to anchor our paper in the real world, I'm going to start with describing a concrete problem, which is discovering population pharmacokinetic models, as has some just presented. So you have just seen Sam's presentation where they used LLM to discover pharmacokinetic models in the form of ordinary differential equations. And I'm going to present a different angle on tackling the same problem and also similar problems, because although I'm going to focus on settings in medicine, our approach will also apply in a variety of other settings I will describe later. But now onto pharmacokinetic models. So just to recap, these models take the patient's baseline covariates such as age, weight, or maybe some laboratory results, the dose of the drug, and the goal is to predict the drug concentration curve over time. And these kinds of models are obviously crucial part of drug development because they allow to understand how different factors impact drug exposure and if any therapeutic individualization is needed. Also, they allow to find efficacy and safety endpoints or if any dose adjustments are necessary. They're also important for clinical practice because recent dosing guidance for some of the drugs actually recommend adjusting the dose of the drug to achieve a target area under the curve from the population pharmacokinetic model. And as you saw, usually this kind of modeling is performed by a system of ODEs and covariate models that map the covariates to the parameters of the ODE. But the question we wondered in this work was, can we actually leverage the recent advances in machine learning to get more accurate models than that? And obviously, there is plenty of forecasting models, and we can use them for the prediction. However, these models are basically black boxes. And as developers, we would like to validate, debug the model, or maybe even certify its compliance with some requirements. And as practitioners, we may be interested in better understanding how various factors influence the prediction. So this is the problem we're trying to solve. And although we used the example where the trajectory is a drug concentration curve, the same applies to other settings. So instead of drug concentration, we could have had a tumor volume or even a survival function, basically anything that is time series. So let's now formalize the problem a little bit more. So in general, the models we consider just take the vector of static features and predict the trajectory that we define as a real function from a specified interval to real numbers. And as I discussed earlier, these settings are frequently encountered in medicine and pharmacology, where where we're interested in predicting the disease progression or drug concentration based on patients' covariates. But these static features can also include the dose or strength of the treatment, or even time and type of the intervention. So basically anything that is static, it may even include one or few initial observations at pre-specified times. And more examples of such scenarios can be found in finance, in time-to-event modeling, or modeling one-dimensional dynamical systems. And in some scientific or engineering domains, time can even be replaced by other continuous variables, for instance, when modeling stress strain curves or current voltage curves. So of course, we have many works that try to provide explanations for the models from explainable AI literature, and they often allow us to answer questions such as how important is a specific covariate for the prediction, or how similar is this instance to other instances in the data set. However, to better understand the models, we may be interested in much more complex questions, such as what would happen to the model's prediction if a specific covariate changes, or how should the covariate be modified to get a different prediction. And now answering these kinds of questions for forecasting models is much more challenging. And why is that case? If we look closer at the questions from the previous slide, all of them require some notion of understanding or measuring the change in the trajectory. And this is much more challenging than in models with single label output. Because if we look at, for instance, normal regression, the output is a real number, and this real number can either increase, decrease, or remain constant. In a classification setting, we predict a particular class, and if that changes, it just changes from one class to the other. Whereas if the label is a whole trajectory, this trajectory can change in multiple different ways if we vary the input. And in fact, answering these kinds of questions with current explainable AI techniques is not very helpful, because all of them represent something that we call bottom-up approach to trajectory comprehension. And now, to illustrate what a bottom-up means, we consider feature-important methods. And although these methods have been extended to time series inputs, limited work has been done to extend them specifically to time series outputs. And in fact, they're often agnostic to the specific type of output. And often the values in saliency methods, for instance, are just calculated independently for different prediction horizons. And this is what represents this bottom-up approach to trajectory comprehension. So it basically means that trajectory is understood by looking at the values of the trajectory at individual time points. So to take a concrete example, we could, for instance, use something like Schaar and get a figure like this, where we get the importance of two static features, alpha and beta, for the predicted trajectory at each time point separately. And this allows us to answer questions such as how important is the dose for the drug concentration at t equal 1.5 hours. In general, we argue, however, that we want to comprehend the whole trajectory at once. So, for instance, when administering a drug, we want to understand we want to understand the entire curve, including properties like peak plasma concentration at the time when it is achieved. So hopefully I convinced you that answering these kinds of questions from the previous slide with the current bottom-up approaches may be very challenging, because the notion of a different prediction based on this individual time points may be either non-interpretable or too simplistic. So now we want to describe the alternative that we propose, which we call top-down approach. So to explain it first, we make the following observation, that humans tend to describe trajectories by referring to the trends and properties it exhibits, rather than just the values it attains. And to illustrate it, we look at 3 examples of trajectory descriptions in natural language. So for instance, if we say the GDP has been steadily increasing for the last 10 years, we have a description of the trend increasing and the description of the particular property of the trend for the last 10 years. Or another example, tumor volume decreases, obtains minimum, and then at 6 months, and then increases. We have the description of the general trend in first decreases and then increases, and some property of this trend, so the minimum is achieved at 6 months. So the top-down approach to trajectory comprehension looks first at the general trend of the trajectory and then at the properties of this particular trend. And this is how we can achieve an interpretable model. So instead of tracking the individual values of the trajectory, as in the bottom-up approaches, we define this bi-level transparency, where on the first level, we track how the general shape of the trajectory changes, and on level 2, we try to understand how the properties of this shape change as we vary the input. So now that we have this conceptual framework with trends and properties, we would like to formalize it. So define exactly what is a trend and what is a property. And we propose to formalize trend using this notion of composition, where a composition is a sequence of motifs, where each motif describes the current shape of the trajectory at a specific interval. So for instance, we can choose a set of 3 motifs, increasing, decreasing, and constant, and then we can divide the trajectory into a few segments so that each one can be classified as being in one of these motifs throughout the interval. And thus we can assign a sequence of motifs to trajectory that we call a composition. So in that way, we formalize trends by compositions, and now we can formalize the properties of a trend as the coordinates of the transition points between the motifs. And now choice of the motifs is application dependent. We describe a few possibilities in the paper, but a good starting point is something that we call dynamical motifs. So this is a set of 7 motifs where the first 3 of them describe straight lines of either positive, negative, or 0 slope, and the next 4 describe increasing or decreasing functions, which are either strictly convex or strictly concave. And what's important about these motifs is that first they encode information about first and second derivatives, which may be important for understanding, but maybe more importantly, the transition points between these different motifs corresponds to local minima, maxima, and inflection points, which are really important for understanding the trajectory. So now I'm going to briefly describe a particular model that we propose in our paper called TimeView that adheres to this requirement of bi-level transparency. So TimeView consists of 2 parts. We have a predictive model and a visualization tool. And due to time constraints today, I'm not going to talk about the actual implementation and how the model is trained. I encourage everyone to look at the paper for the details. But today I'm going to just describe how this model is actually used in practice. So let us see how the visualization tool actually looks like. So we consider a problem of predicting the trajectory of tumor volume based on patient covariates and the dose of the drug. And now our visualization tool consists of these 3 parts, where in the left panel, we have a movable slider for each feature that changes the predicted trajectory at the center. Now, the colors on the band below the slider signify the composition of the trajectory if the feature is in the corresponding range. And this allows us to understand how the trend of the trajectory changes as we change each feature. So this is level 1 of bi-level transparency. And now to understand the properties of this trend, so on level 2, we choose any of the transition points in the central plot, and then we can analyze its position with respect to any chosen feature on the plot on the right. So it currently shows how the y-coordinate of the second transition point, which corresponds to local minimum, increases as initial tumor volume increases. So now I will quickly show how we can answer many meaningful questions about our model using this interface. So consider the question, would the predicted tumor volume keep decreasing if you adjusted the treatment? Now, this is a question on level 1 about the trend of the trajectory. So the center plot shows that the current trajectory is decreasing. The colorful band under the dose slider shows that the compositions for different drug dosages. And now we can see that the trajectory is increasing for very low dose, which is in color orange. For higher dose blue, the trajectory is first decreasing and then increasing. And finally, for higher doses, green and pink corresponds to decreasing trajectories. So now to answer this question, it is just enough to check at which point the bands change color. So if the drug's dose is kept above 0.46, the trajectory will keep decreasing. Let's consider a different question. So what feature changes would lower the minimum tumor volume? So this is a question on level 2 about the property of a particular trend. So let us consider a lower drug dose where the trajectory decreases and then increases. We observe that the minimum of tumor corresponds to the y-coordinate of the second transition point. And now we can use the tool on the right to plot how this minimum depends on the dose or basically any other feature. And we can see that in this case, the minimum volume decreases with the increased drug dose. We can also change the question slightly, and we can consider the time when the minimum is achieved. And we can easily do that by just switching from the y-coordinate of the transition point to its t-coordinate. And we can see how the time depends on the dose of the drug, or as I mentioned, any other feature for that matter. In all these examples, we could see the effect of changing one feature at a time, but we could also visualize the effect of changing 2 features at a time using this kind of control plot, where each color corresponds to a different composition. So now it is clear how changing the features influences the composition of the trajectory. So now TimeView proved to be a very powerful model, offering performance comparable to black box models while allowing for much more transparency than the current methods can offer. But another interesting application of the whole framework is to provide more meaningful explanations for black box forecasting models. So as I mentioned before, we could apply the current XAI techniques to provide explanations at the individual time points. For instance, we could apply Schaar to the predicted value at t equal 1.5. To get the importance scores for the prediction on this particular time point. But then, can we get more meaningful explanations? Let's start with any black box forecasting model. The output of such model is a trajectory. What we can do now is wrap our framework around that model so that apart from the trajectory, it also predicts two additional outputs, the composition of this trajectory and its properties. And now what we can do is, instead of applying XAI techniques to the values of the trajectory, we can apply them directly to these additional outputs. For instance, we can apply Schaar to get the most important features for predicting the shape of the trajectory, or we can try to fit a static transparent model like linear regression to any of the properties of the model. For instance, we can approximate the maximum of the trajectory as a linear equation. So now, in terms of the implementation, TimeView together with the visualization tool is already available on our labs repository, and we're currently developing a nice, easy-to-use Python package that you can wrap around your favorite forecasting model and your favorite XAI technique and obtain this kind of meaningful explanations. We hope to publish it in the next month. So I hope you enjoyed this brief presentation. I encourage everyone to take a look at the full paper. I would like to thank Roche and AstraZeneca for funding this research.
Good afternoon, everyone. So I'll be kicking off the next section on making AI and ML work in the real world. So my name is Nabeel Seedat. I'm a final year PhD student in the lab, and I'll be talking about some frontiers in data-centric AI. So we've really seen data-centric AI in the last few years really be this paradigm shift broadly in the machine learning community. And being this shift of thinking on how we approach machine learning has really required working on novel ML research to really bring this agenda to reality. 3 years ago, when we started embarking on this agenda, the lab, or the Van der Schaar lab, was one of the few in this research area. And what's really been encouraging over the past 3 years, we've really seen like a burgeoning of research in this area at the top AI/ML conferences, the NeurIPS ICML iClears, with dedicated tracks to data-centric AI, as well as workshops, as well as a new journal coming out. And it's really encouraging that we've seen the machine learning research community really pick up this area over the last 3 years. And to really give you a flavor of what we really mean when we're talking about data-centric AI, particularly in the lab, is really data-centric AI encompassing developing principled machine learning methods and tools to systematically characterize data sets, evaluate, and generate the underlying data used to both train and evaluate machine learning models. And this is really the idea of what we've tried to push forward in this agenda more broadly as a lab over the last 3 or so years. So when we just kicked off this agenda quite early on, we really put together this manifesto piece called DC Check, which is a data-centric AI checklist together with Fergus Emery, who was a postdoc in the lab, and Mihaela, where we really tried to understand and put forward to the community where we see data-centric AI really going and what are the real challenges faced by the research community, both what tools exist, but also what the community as researchers need to work on to really bring this agenda to reality. And we really looked at trying to show data really spans, and its importance spans beyond just the data preparation step really being static and once off. Really, how can fundamentally thinking about the data and building fundamental tools around data really affect how you train models, and how do you informatively train models with this knowledge of data? How does data affect testing models and stress testing models? And how does it actually affect deployment of models at deployment time and actually having them continuously retrain or have trustworthy predictions at the end? And what we produced with DC Check was a checklist style framework for practitioners and researchers to really say, have you really thought about many of these considerations? What exists from a tooling perspective and what research opportunities are there? But we then wanted to take it a step forward after 2021 and 2022, when we put together this manifesto piece, was really to say, how can we make this more than just a manifesto and really bring this to life? And actually, we started building out many tools in this area, and I just want to highlight some of them that the broader research team working on data-centric AI in the lab has really worked towards. And I'll highlight in bold many of the works that have come out over the last year. So the first has really been around dataset construction and harmonization. So whether you have unlabeled data, whether you want to do active learning, whether you want to do data harmonization, we've done a fair bit of work, especially in the last year, around that. We've then really started trying to fundamentally understand, can we build principal machine learning tools to really audit and characterize datasets, really to understand what data points are going to harm or benefit machine learning model performance, and how do we do this in a systematic, automated manner using machine learning tools, and then using this understanding of the data to actually inform how do we robustly train models to perform well on subgroups or when we move them across domains and distributions. We've then also done work in the uncertainty estimation area around conformal prediction, particularly how can we leverage unlabeled data for that purposes of informing uncertainty estimates. And then in terms of a deployment setting, we've really done some work of saying, well, data often isn't static. And when we're deploying machine learning models in real world systems, the data is of course going to change over time. And this started with our first work of data suite in ICML, and more recently diagnosis, where we looked at it from a causal structure perspective. And then from a deployment perspective, also that given the model performance might actually change over time, how can you have a self-learning or self-healing system that can actually address shifts and drifts over time? And can the system automatically decide what it should actually do to actually ensure robust model performance when deployed in the real world? And then really we've done a lot of work in the lab broadly on synthetic data, really on synthetic data to improve data sets themselves, but also more recently, synthetic data to actually stress test machine learning models to actually understand at deployment time where we don't have a lot of data on small subgroups, where models might fail. And more recently on the testing side, we've also used large language models to understand how do we systematically better test performance of different subgroups. But of course, this is a lot of work that you see on this slide, and we don't have a huge amount of time. So I'll be talking about today a work called Curated LLM or CLLM, which is really a synthetic data work for small data regimes. So we really started thinking to ourselves, how do we actually do machine learning in these very ultra low data regimes? This is actually has been quite a challenging problem for the broader machine learning community, and we didn't have very satisfactory solutions, where we all know that machine learning presupposes access to vast amounts of data if we want good model performance. However, we are also hamstrung in many settings where we are sample constrained. When we think of healthcare settings, when we think of pharmaceutical settings like in clinical trials, and we think of low resource settings, so settings across the globe where we're lacking digitization of, for example, an electronic health record. If we do want to get access to samples, we might only have sometimes less than 100 patient samples to actually do our machine learning task. And of course, this is going to be really suboptimal for machine learning. And the reason for this is we simply lack diversity in our patient population to actually learn robust and generalizable models that actually generalize when deployed on the population. And we thought to ourselves, how can we actually solve this? And do advances in foundation models and large language models really help us to actually solve this problem, which has proven quite challenging for many, many years? And we've really looked at the problem of, can we make data augmentation really work? And we know that synthetic data has widely been used for data augmentation. However, current and especially tabular generative models, so whether it's your GANs, your VAEs, your diffusion models, your normalizing flows, all of these generative models will really struggle in these ultra low data regimes. So we have less than 100 samples. And the reason that these models will really struggle is if we only have 100 samples, these models can't really extrapolate beyond this data manifold that we've given of these 100 samples to learn. So even if we generate more synthetic data for augmentation purposes, we really don't get diversity that we actually care about if we want models to actually generalize. And the idea that we have is, can large language models really help us to generate diverse tabular data sets? So electronic health records, or in a clinical trial setting, can a large language model help us to just generate diverse tabular data on top of which we can then build machine learning models? And of course, you might say, this sounds a bit crazy, and we know that LLMs are not going to be the silver bullet, fortunately. So we might get diverse data from a large language model. So if we ask a large language model to generate synthetic data for us, we might get a lot of diversity because it's not constrained by this manifold of the data that we've been given it. But at the same time, we might also get data which is just fundamentally hallucinated, incorrect, doesn't capture the correct properties from feature to label, so your Y given X relationships. You might have all of these challenges. And the question then becomes, how do we balance the risks and benefits of LLM-generated data? And we really said, can we answer the more fundamental question of how do we ensure high-quality LLM-generated data, or really more generally synthetic data that's reflective of real data? So when you have a lot of data, this is quite an easy task because you can have a held out real data set, you have a lot of data, and you can compute any of your statistical fidelity measures on top of that data. So that really is typically a solved problem. However, when you have very little data, those performance estimates from these statistical fidelity measures are not going to be really that reliable. So how do we actually ensure that what the LLM has generated is actually reflective of your real data? And for this here, it's a work called Curated LLM, the synergy of LLMs and data curation for tabular augmentation in ultra-low data regimes. And this is joint work with Nicola, Boris, and Mihaela, and we presented it at ICML 2024. So really the idea of curated LLM, and I won't go into too much technical details, there'll be a lot in the paper. I think we really wanted to share a lot of insights of what we got in this presentation. But really, to give a high-level overview, we start with a very small training data set, so dtrain. We then provide contextual information to a large language model, so descriptions about the data, any prior knowledge that we have. And we can leverage the few-shot learning capabilities of a large language model by providing our very limited examples as in-context demonstrations to a frozen black box LLM, and we can ask it to generate a huge amount of synthetic data. Once we have the synthetic data, of course, the job is not done because, as I mentioned, how do we know what we can trust? We then train a curator model, which I'll discuss more on the next slide, where this curator mechanism is trained on the real data. We then assess every synthetic sample with respect to this curator model. And on the basis of these learning dynamics, we then select samples which we keep and some samples which we discard, and we produce a curated data set on top of which we can train a downstream predictive model. So any machine learning model that you fancy. So how does this curator mechanism really work at a high level? I've left all the mathematics out, and you can see that in the paper. So it's really which synthetic samples are good with respect to real data is the question we're trying to ask. So really what we do is we assess the learning dynamics of synthetic data on a curator model which is trained on actual real data. And the high-level idea of this is that if samples match the learning dynamics of your real data, which you hope is representative of the population that you care about, these synthetic samples are probably samples you actually want to keep and are good and representative of your population. And those where over these model checkpoints, the model is really bad at dealing with the synthetic data. It tells you there's something very different in the learning properties of these synthetic samples. And we use an uncertainty estimation lens to actually say, how can we actually curate out which samples are these really bad samples where the dynamics really don't gel with the real data? And then the output of this here is really a curated data set. And I encourage you to take a look at the paper for specifically more details on like our metrics and how we do the actual curation step. But what we really wanted to do is really highlight insights and what are the real benefits of this. So overall, LLMs plus curation really, really help a lot to guide you through this very big set of numbers. So what you see on the right is firstly, compared to any of your baseline generative models that you might have used in the past, so your GAN-based models, diffusion models, normalizing flows, VAEs, we see that curated LLM plus our curation mechanism really outperforms these methods, which are really then constrained by your small data set. So in this case, 20 samples or 40 patient samples. What we though see, which is most interesting, is beyond the curation mechanism and a GPT-4 type of LLM really helping improve performance. What's super interesting is that even on 20 samples or 40 samples, we not only achieve really good performance, which is higher AUC on a downstream task, but we also hold out what we call an oracle data set. So this is, imagine you had access to 2,000 or 3,000 patients. This is your upper bound of performance that you can achieve on this task. And we see that actually the downstream performance with our curated LLM, which only had access to 20 and 40 samples, is particularly actually quite close to this upper bound oracle that had access to all of the samples, which highlights this difference of we being able to generate diversity as well as keeping the right diversity in the dataset. Also, if you're very interested in using other LLMs, we've also tried this on open source like your Mistrals and Llamas, and many of these results still very much hold for other language models. So you might say this is a bit crazy. Why does this even work in the first place? So we wanted to highlight the first insight, which is really the LLM plus the curation mechanism really has the capability to extrapolate to regions of the manifold with no training data. So you can see in light blue, so this is this oracle I mentioned, all of the data that you might have held out that's representative of the population. You can see we have little black dots, which is our very limited training data set. And we can see that the LLM is able to GPT-4 in red actually generate data in regions where we didn't have training data, especially in contrast to a VAE, which simply just can't have this extrapolative property. So you can see it over there as highlighted on the screen. So that's the first reason why the method even works in the first place. We also then looked at who do we really benefit the most? So where is this performance gain really coming from? So we actually looked at a deep dive into demographic subgroups on datasets that actually saw the largest gains. So these are actually groups in the training dataset, so your very, very small training dataset where we just didn't have a lot of samples. And then when we take them to our population at deployment time, these are the groups that actually see the most benefit performance-wise. And this logically makes sense because we're really able to extrapolate and produce good samples in these regions where we didn't have a lot of real data to start with in the first place. So really, from a machine learning trustworthy and reliability perspective, it really is benefiting all of your subgroups, especially your much smaller demographic subgroups that machine learning typically struggles on. And then finally, from a more technical perspective, we looked at what is the curation mechanism actually doing from a distributional perspective. And we actually looked at curation really aligns our real to synthetic data sets. So this Y given X relationship between the distributions, that the samples that we actually discard are actually those samples which really don't have this correct Y given X relationship. The LLM is probably just made up or hallucinated these. And those samples which our curation mechanism actually keeps in place are those which have the same properties of the Y given X of our original data set. So this is really an understanding of why this works. And then finally, before ending, you might say, well, I've generated a data set. I only have to train a machine learning model, and then I have to take it to real data to test it before I know if this LLM has actually generated data well in the first place or not. And we tried to answer this question and say, can we know the data is poor quality a priori? So before having to put in all of the effort to train a model and then go validate it on the population. And we tried to produce a proxy of can we flag poor generation in this like hallucination from a language model. And what you can see on the screen, so on the y-axis, these are for all the different sample sizes, but on the y-axis, we looked at area under the receiver operating curve on the test set. And then we look at, for different data sets on the x-axis, the proportion of samples that CLM's curation mechanism is actually removing from the data set. And we see quite a strong relationship where by curating, if we discard many, many samples, this is going to be quite indicative of poor test set performance. And if you're probably keeping a lot of samples, this probably means you're going to do really well. And it kind of shows you, or at least provides some proxy to a human being or a practitioner, that when using a method like CLM, they can already see if you're going to throw away a lot of data, you probably should expect poor downstream performance on your testing set. So at that point already, you can already flag where the LLM is really good and where its prior might be really good to actually help you and where it might actually struggle. And to end off, if you do really want to learn more about this broader data-centric AI, as Mihaela mentioned, please check out our tutorials from IJK, NeurIPS, and MICAI, which are online. And I'd really like to thank the Cystic Fibrosis Trust for really sponsoring all of this research and making all of this possible. Thanks so much. Now I'd actually like to hand over to Sam to take us away with L2MAC and LLM code generation.
Brilliant. Hi. Yep. So yeah, this is L2MAC. So this is large language model automatic computer for extensive code generation. And really what we were excited about is the first von Neumann architecture to extend LLM capabilities beyond the inherent context window limitation, which we're going to. So this is joint work with my excellent co-author Max and my amazing supervisor, Mihaela. So let's situate this in a bit of history here. So actually this work was done, published in iClear this year. And actually you can see when the paper was originally released on arXiv, actually we were, for a brief point, state of the art for human eval code generation. However, I'll be honest, now there is better coding models that actually work on this benchmark, but you can see just a bit of history here. And this is really where we're presenting today, but a lot of the approaches which we talk about limited context windows apply to many open source LLMs and also larger LLMs. So what is the inherent problem with large language models today? So of course we know that they're incredibly useful and really have opened up many unique applications, such as a lot of the work just presented in all the presentations thus far. However, they're fundamentally constrained by one big key limitation. That is, they have a fixed context window. And what does this mean? I mean that they can only have process so many input tokens, where you can see input tokens here represented with, say, individual words, but actually in reality, it's actually byte pair encoding input tokens. And for essentially the old versions of language models and even the open source ones, you're often limited to having a fixed context window. In this case, say GPT-3 had a fixed context window of 1,024 tokens. And GPT-4, the early version, was about 8,000 tokens. And of course, we have a larger token window now, but of course, it's expensive. So this work aimed at looking at creating a von Neumann architecture to actually overcome this challenge, to work with a limited context window LLM to allow it to generate larger outputs than, say, beyond that context window limitation constraint. So where is this immensely useful? A number of applications, but one of the key consideration, most real-world impact ones, is generating large code bases, which we'll go into. Now, we can see actually a description of a LLM benchmark task for, in this case, human eval, which is a question and answering of small code generation snippets at about essentially graduate level or undergraduate level of code generation problems of, say, creating a sorting algorithm. And most LLMs, especially closed source LLMs, are very good at this problem. As we can see here with one of the actual benchmark evaluation problem sets, and then most LLMs will respond with some sort of algorithm implementation, which is correct. However, we look at the problem where can we actually get an LLM to generate very large, extensive code outputs, which is significantly beyond the context window limit constraint. So what does this impose? This means that we can actually create more content than the context window constraint, because these models are autoaggressive, they have to feed back into themselves. So we need some sort of framework for such a LLM to operate to do this. And really, at the moment, without such a framework, you're limited to either the context window or actually cutting the previous content generated, which, as we'll see, leads to issues. And this work, we propose a automatic computer framework or a von Neumann framework that treats the LLM as a processor and can actually run through essentially sequential instructions, loading them into the LLM when needed, and leveraging an external memory base. So let's look at some of the related work, leveraging external memories with LLMs to get around some of this context window limit constraints. So current memory augmented LLM approaches cannot handle extensive generation tasks, since they really only focus on reading memory and reduce its evolution to the concatenation of new memories. This makes memories irreversible and prevents adapting previously generated outputs as the task progresses. And really, this is a limitation of any autoaggressive probabilistic model. And really, a lot of these existing approaches use tools with the LLM to actually interact with some sort of specialized memory to maintain, say, precise values for variables. For example, dictionaries or databases, we can update database records, but really they're inherently just limited to that application. And really, we want some sort of free, rich form text description that can actually handle external memory, in this case, code. So compounding both of these shortcomings, memory-augmented LLMs do not include memory or mechanisms to maintain syntactic and semantic consistency within the external memory, a vital requirement for generation of coherent and interdependent extensive outputs, such as generation of entire code base or entire book. So in this case, we introduce a framework, the Large Language Model Automatic Computer Framework, or we call it L2MAC. Now, really, this is the first practical LLM-based general-purpose stored program automatic computer or von Neumann architecture framework, an LLM based multi-agent system for long and consistent output generation. Its memory has two components, the instruction registry, which is populated with a prompt program to solve the user-given task, and a file store, which will contain the final and intermediate outputs. Each instruction, in turn, is executed by a separate LLM agent, whose context is managed by a control unit capable of precise memory reading and writing to ensure effective interaction with the entire file store. Now, this brings immediate benefits of strong empirical performance. It was state-of-the-art in previous, however, this benchmark has almost been solved now, very much similar to the ImageNet moment of vision models. And at the time of the ranking, it was currently roughly about third. And we can also generate large near unbounded length outputs, significantly bypassing the finite context token limit. And we can produce detailed outputs that fulfill complex user-specified requirements, and we can automatically error correct generated outputs such as code that has syntactic and functional errors. And we can correctly condition on and integrate with existing previously generated outputs. So let's look at a walkthrough example to really understand how this works. So a user will come along with a requirement to, say, in this case, code something for. So code an online chat application with individual features. And the LLM will actually, almost like a computer, generate a prompt program, or in this case, a set of sequential instruction steps. Now, each instruction step will then be loaded into a fresh context window with the instruction step. And we actually use a finite state machine to actually manage the loading and unloading within the context window, and to actually load individual instructions in, very much like a computer framework on a von Neumann architecture operating with a limited context window. In this case, the LLM actually is imbued with tools to read and write general purpose Unix files, in this case, the code files. But it can also be generalized to, say, just text and files as well, as we'll see later. But in this case, we have code files. And in this case, the LLM has actually written two files. And we specifically instruct it when it's generating code to generate tests. And these really create functional tests, which we can test the code that's already generated as it evolves over time, as we'll see. So the finite state machine actually does code checks to check that this code is correct. And with code, you normally have syntactically correctness. So is there any missing semicolons? Does it actually pass linters? And then you also have functional correctness, which is, does the code actually pass its unit tests? So both of these features have to be correct. And then the finite state machine will also check with the LLM, asking it has it completed the instruction. This is really avoids, say, hallucination or just it not actually completing the current instruction. So it has to reflect and actually say, has it actually set up this correct instruction? If it has, then it summarizes, and the summary is then sent to the next instruction, and the context window is clear with the next instruction. Most crucially now, the LLM actually is also given information of what the individual file names are called, and this roughly corresponds to the actual functionality. So given this, the LLM can then actually request to read files into its context window that it might think might need to see. So in this case, it actually has read app.py, because to create some sort of additional functionality or features, it then needs a condition on the existing code and override it or augment it. In this case, it's actually added additional functionality to this file. Now, what's interesting, this has then broken some functional tests which are already in the code. So these test errors are then iterated with the LLM to fix these errors. In this case, it's actually gone up and updated its memory structure until it's in a fully functional working complete state. And this process is iterated over a number of instructions or iterative steps until we actually end up with a large code base, which is coherently independent and also works coherently, as we can see here. And it's also able to generate different code files such as HTML files or JavaScript files as well. Now let's look at the finite state machine. What makes this possible? So we really represent the LLM as a processor, and we leverage tools for it to read and write a memory file store, and also individual checks for actually checking whether the state has been completed and to evaluate the memory as well. And this really generalizes to other domains as well, which is nice. And we have a way to actually handle when the context window limit is reached. We can actually summarize the current progress and then continue from where we left off with a fresh context window, or if the instruction step was complete, then load in the next instruction step to execute. And really, the key thing here is doing syntactic checks for coding and also functional tests and unit tests to actually coherently, at least the first step, check, especially code or memory that's been generated a long time ago, is correct. So when we compare this with existing memory-augmented LLM approaches, you may be familiar with, say, AutoGPT. This is a variant of autonomous agent LLMs with memory, or single LLMs, such as GPT-4 or other closed source versions, or even reflecting LLM frameworks. We actually see that we can correctly handle context, which we'll go into in a minute, and we can also precisely read and write an entire memory store, which we'll go into a minute as well. And we can obviously check the generated outputs as well. So really, it's the first method that can produce detailed extensive outputs that fill complex user-specified requirements in the input prompt. Whereas autonomous LLM agent LLMs, such as AutoGPT, with memory immediately summarize the user's input prompt into a few sentences or goals and consistently summarize their past actions when following these goals, leading to forgetting exactly which files they've residually created in the past and a loss of user-specified requirement information to implement. So looking at across different tasks, we also in the appendix provide more problems to look at, but we actually take system design problems and look at generating large code bases from these and compare the existing baselines against this. What we see is we can actually achieve a very high percentage of feature fully implemented within the code bases compared to the baseline approaches. We can also generate a fairly large amount of lines of code as well, whilst also generating self-generating unit tests that also pass, which is promising, whilst also generating, essentially in this case, 0 functional errors within the code. And we can fully implement the highest percentage of user-specified feature requirements across all tasks by generating fully functional code that has minimal syntactical errors and a high number of self-generated unit tests. Therefore, at the time of this publication, CodeL2Mac was state-of-the-art for completing the systems of designing large code generation benchmark tasks. Now, if we compared it against the existing approaches at the time, we saw was actually on HumanAbout got quite competitive performance. Now let's go to the inside experiments. So CodeL2Mac can correctly perform task-oriented context management, and we can empirically observe that CodeL2Mac can retain a high number of requirements within its instructions and perform instruction-oriented long-running tasks. As we can see here with the actual where we can actually, over the course of episode duration, we can measure how many of the feature requirements are actually kept within the LLM instructions, if you will. Unfortunately, AutoGPT actually summarizes a user input prompt into about 3 or 4 high-level goal sentences, actually lossily compressing and losing important contextual instructions to implement, such as features. Whereas CodeL2Mac can actually take a very detailed feature requirement list and store them in the instructions and actually understand this and operate this throughout many instructions. Most importantly, we ask the question, can actual framework like this actually have a good understanding of all the memory, particularly outputs generated from very long instruction steps ago? And the answer is affirmative, yes, which is promising. And how we do this is it can actually understand the existing code files generated many instruction steps before, read these, and then update them. So what we see here is a visual histogram of the different unique files on the y-axis and the episode environment steps on the y-axis. And in this case, white is a file existing, and then red is the file being written to, and blue is the file being read from. Compared to an autonomous LLM GPT agent, which actually, due to its finite context window, when it creates files and then iterates more iterations, has to almost cut off the previous information within the context window. So what that means is it forgets the files it's created, creating duplicates of the same file and just actually not reading the same file to integrate it into new code files, because really an entire code base needs a condition on the existing code that is generated. So this means actually AutoGPT consistently creates the same files and can get lost. Whereas actually, say, CodeL2Mac can actually read files and consistently update them throughout the whole instructions of the episode duration. As we can see here in the very bottom, in L2Mac, it's able to read and write files throughout the course, which is really key. And this is far beyond the context window limit, which is very promising. But given this, can it actually check the generated output? Because as we know, LLMs hallucinate. They can actually create code errors, either functional errors or syntactic errors, because they're really a probabilistic generative process. And the answer is yes. I mean, naturally, errors do occur,
but actually by having these code checks of syntactical and also functional correctness, when these errors do arise, they can be iterated with the LLM to then be solved. As we see with this histogram of code errors over the episode duration, errors do arise, but they can be quickly resolved. Whereas such a method like AutoGPT, when errors do arise, unfortunately, they can actually, AutoGPT can forget about files that's created many instruction steps ago, which are actually outside the context window, and so therefore those errors can compound over time. So let's talk about some of the contributions. So L2MAC is the first practical LLM-based general purpose stored program automatic computer, a von Neumann architecture framework, an LLM multi-agent system for long and consistent output generation. It uses checks such as code checks to correct generated code that has syntactic and functional errors within, whilst conditioning on and integrating with an existing code base. Empirically, L2MAC can generate large code bases to solve for the first time high-level system design tasks of creating entire applications and where we observe that it's state-of-the-art. This now enables a practical tool for large output generation, such as code bases or entire books, and to execute long-running, large unbounded output tasks with an LLM as an AI assistant. And actually, we provide a very nice GitHub open source repo, which I encourage you all to check out, and also a lab GitHub repo where you'll find all the code for the existing papers from the Van der Schaar lab. And we also provide a documentation website as well. And you can get used to running the code right now by just running pip install L2MAC and then giving a prompt. For example, you can ask it to create a playable snake game. And what it will do, it will actually then in your current directory, actually output all the code in Python to do this exactly. And then you can run this code and you can play a snake game right on your computer right now. What's promising is it can do more than just create toy problems. It can also create initial versions of, say, a complex web application with a UI front end and also working backend database, a mock database in this case. So we created a URL shortener application, as you can see here, which fully works. And we can also go beyond things than just coding, which is very exciting. And I encourage you to check out. You can also ask it to potentially generate an entire book from a single prompt. So in this case, we generated a Italian pasta recipe making book, and it was able to generate, in this case, a multi-chapter small novel book length, which was coherent and had actually generated the chapters and read previous chapters to make sure everything lined up correctly, which is also available on the website. And I'd like to give a huge thank you to the sponsors, AstraZeneca, to make this possible, and also encourage you to check out the paper on the left-hand side or the code to run this on the right-hand side. Thanks so much for listening.
Okay, so hi everyone. My name is Tennison, and I'll be, thanks for coming to the open house today, and I'll be giving the following presentation. And this is work done jointly with Sam, who you heard from just then, and supervised by Mihaela. And the title of this talk is Learning Hybrid Models for Digital Twins of Dynamical Systems. And it will be presented as a spotlight at the upcoming conference in 2 months' time. Cool. So we start off with a little bit of background on dynamical systems. So what are they exactly? They are models that describe how variables evolve over time. And they are pretty important for a wide range of applications, including predicting disease progression, treatment strategies, and improving patient care. And formally, we can say that a dynamical system is system S with 3 components. X is the state space, or the space of set of all possible states that a system can be in. A U is the action space, where a particular U is a particular treatment or a particular action. And phi here is a dynamics or an evolution function, which given a particular state, action, and time point, it can output a distribution over next states. And some examples of dynamic systems that are commonly encountered in the healthcare sort of domain include the sort of SER models, which are epidemiological models that are used to predict disease spread, PK/PD models, drug responses, and tumor growth models, and yeah. And digital twins are essentially computational models that aim to approximate dynamical systems. And here we have denoted a digital twin as F with 2 subscripts. And the reason why we do this will become a bit more clear later. But theta essentially is the model specification, which is the structure and form of a model, and omega theta is used to denote the corresponding set of parameters for a particular specification. And an effective digital twin is pretty useful for answering certain questions. For one, it can help us understand future outcomes, like what is the future spread of a disease. It can help us understand how a system is going to change, like how would disease dynamics vary with different subgroups. And it can also be used to simulate different types of controls to understand the impact they would have on a system. So in line with that, we've sort of formally defined 3 key desiderata that a digital twin is supposed to, an effective digital twin should ideally satisfy. And the first one is the ability to generalize the unseen state action distributions. So this is sort of a little bit of a departure from traditional machine learning, where machine learning models are often expected to be deployed in settings where the data that you receive is ID to the data that you have at training time. Whereas with digital twins, a lot of the time, you are expected to simulate things that have not been observed during training, so different state action combinations. An example of this is like, can a digital twin trained on adult patient data reliably predict drug responses for pediatric cases? And sort of related to that is the importance of sample efficient learning. And this is really the consideration that we want to be able to learn accurate dynamics given only a very limited data set. And in the real world, for example, we often have less than sort of 100 or 1,000 examples. And this is not exactly the ballpark, in the ballpark of numbers that are required in modern deep learning to learn an accurate model. And last but not least is the idea of evolvability. So this is meant to reflect that this underlying system that is being modeled itself can change over time. So the twin should be easily evolvable to reflect these underlying changes. And some of the changes could include, for example, new bacterial strains or evolving resistance patterns. So we want the twin to be easily updatable to reflect these underlying changes without completely retraining or coming up with a new model. And sort of a brief view of what existing methods do to address these desiderata. So one, they can largely be sort of categorized into 2 approaches. The first one is sort of a mechanistic approach. And essentially what this does is it comes up with sort of like closed form equations that are usually based on known principles to model a system. So for example, here I've shown like a pretty well-known SIR model. And the good thing about these is that they can generalize quite well, especially when they're like correctly specified and they correctly capture the system dynamics. And the flip side of that is if it's incorrectly specified, especially in cases where the knowledge is incompletely incorrect, then these models don't do all that well. And on the other side of this are more sort of deep learning, machine learning kind of approaches, where you sort of have a black box and you want to learn the system dynamics directly from data using usually a neural network of some sort. An example of this is like a neural ODE. And the good thing about these are they're purely data driven. So you don't really need that much assumptions about how the system is behaving. And you can model very complex patterns that is very difficult to capture with mechanistic modeling. However, they are more sample inefficient, and because they're usually monolithic models, they're very difficult to continuously update and to reflect underlying changes. So the high-level motivation for our work is whether we're able to combine the strength of mechanistic and neural models to develop a hybrid model. So a hybrid model is essentially just a composition of these 2 components, where the mechanistic component is used to symbolically encode some sort of domain knowledge. And this can improve sample efficiency and serve as some sort of regularization to help it generalize better. And the neural model is used to capture more complex temporal patterns that the mechanistic component might, especially in areas where the mechanistic component might not be accurate or might be incorrect. So hybrid models have been used to some extent, but largely they are created by human experts. And this is sort of a tedious and approach that is not very scalable. So in this work, we sort of really want to see if there is a way where we can automatically learn hybrid digital twin model. So that's the research question that we were interested in, and to sort of further sort of describe how we approached it, we can sort of think about the process of constructing a hybrid model as involving 2 stages. The first stage is about coming up with the right specification. So this is where we come back to the subscripts. So theta is about, for example, the neural architecture for the neural component, or the functional form and structure for the mechanistic component. And then for each specification, you have a corresponding set of parameters. And this would be the set of vector of weights and the coefficients that go into that define the symbolic components. And translating this into sort of a mathematical problem is one of the more obvious ways to do it is we can sort of see it as a bi-level optimization problem. And that's sort of described here. And essentially, you have an upper level problem where you want to find the optimal specification with respect to some outer level loss. And here we sort of define that as just the generalization performance of a digital twin. And the inner level objective is to find the optimal parameters with respect to a particular specification that maximizes an inner loop loss. And here we've defined that as training set performance. So this is somewhat easier said than done. And if we just sort of look at that sort of mathematical formulation of the problem, there are two main things that pop out. The first one is how do we automatically encode the correct domain knowledge automatically? And the second one is especially the upper level search space is of model specifications. That's a very large and combinatorial space. And if you think about it, it's basically the space of any possible hybrid model that could be developed for a particular system. And in some sense, you cannot manually specify the search space, and it's very important that you search through it efficiently. Cool. So the way we approach this is we've sort of developed a novel evolutionary framework. And an evolutionary framework is sort of just some sort of search framework inspired by principles of natural evolution. And we'll sort of go through that more concretely later. And we use the evolutionary framework to design digital twins using large language models. So here, what the large language model does is it acts as a general model, and what it iteratively proposes new specifications of digital twins. And these specifications are represented in a code format. So it's sort of, that is sort of like a formal language representation. It looks at the code, which corresponds to a specification of a particular model. And these models have parameters that are not yet optimized. And what we do is we take this specification and then we do offline optimization of the parameters using the training data set. And once the optimization is done, we have a fully sort of functioning model. We evaluate it, and then we have a second LLM. And this second LLM is used to evaluate the performance of the digital twin and provide targeted improvements for what can be improved in the next round. And this continues over multiple steps. And we see that it sort of comes up with better and better models, and we can sort of keep running this until we have a model that we're satisfied with. Okay, so here's a visualization of the approach. It is pretty involved, but the idea is fairly straightforward, and we'll be stepping through it. So the first part is basically how this whole iterative loop is initialized. And it begins with a human user providing two things. The first thing is what we call a modeling context, and a superscript context. And what that does is it's a natural language description that describes the system, its variables, the task, the metrics, and what's being modeled. And then also some sort of data that we split in the validation set. And given this information, in each iteration, the modeling agent is tasked with generating a novel model specification. And it has access to the modeling context as well as a set of top K past models. So in the first iteration, this set will be empty, but as we go on, this set will be populated by high-performing models that have been discovered in the past. And it also has the most recent evaluation feedback, which is provided by the evaluation agent. And once the valid model is proposed, then we optimize it offline using for example, stochastic gradient descent and some other optimization tools. And then we get sort of a specification with optimized parameters. And what happens next is this functional model is passed into the evaluation stage. And here, this is sort of a fixed evaluation routine. And we basically evaluate two things. We evaluate the overall performance of the digital twin on the test set. And we also evaluate the component-wise performance. And each component is just sort of one state variable. So imagine a system with 3 variables, and you also see how it does in terms of each variable. And once the evaluation information is obtained, we use this to update the population. And essentially, we do a selection step that looks at the models that have been generated in the past and the new model, and it only retains the best ones, the best unique ones. And the last step involves an evaluation agent. So the evaluation agent receives this pool of models as well as the instructions from the user. And what it does is it provides some textual feedback on what exactly needs to be improved in the next iteration. Yeah, so to put all of that into more sort of concrete terms, we sort of have this following demonstration, and we sort of really look at how a model was evolved, which sort of relates to the third desiderata that we mentioned at the start. And in this figure here, we have a Pareto front of the evolved hybrid digital twins. And what we see is that the validation performance continuously improves over time. And we've also annotated sort of what is being done based on the feedback from the evaluation agent and a sort of corresponding a manual examination of what how the model has been changed. And for example, here it adds a logistic factor to model tumor volume. And yeah, updating the black box MLP, which is a neural component to model residuals. And yeah, so overall, this looks pretty promising. And one thing we want to highlight is obviously in each iteration, in the feedback provided, we can easily incorporate expert feedback as well. So then we can have an expert in the loop who is sort of providing their own judgment and evaluation, and using that to steer model development. And on the quantitative performance side, we start by looking at how accurate or the simulation performance of the evolved models. And we start by looking at in-distribution data, so where the test data is drawn from the same distribution as the training data. And we compare against the range of different neural and mechanistic models. And we highlight here that we also have methods like Cindy, which is a discovery technique. And what it does is it discovers a mechanistic model from data using machine learning. And we find that overall, like the evolved models that our framework comes up with is able to model a system more accurately and achieving the lowest simulation error. And then moving on to the more interesting stuff, which is how it generalizes out of distribution. And here we see much more of a performance gain. And we see that compared to existing methods, especially neural network-based methods, the out of distribution performance is significantly better. And this is likely due to the neurosymbolic composition in the evolved model. And going to the second desiderata, which is about how efficient the learning is. And what we did here is we sort of gave each model a different sort of budget of trajectories that are available for training. And we find that across this entire range, the hybrid digital twins are especially sample efficient. And this is likely because as the model is being evolved, proposed models that are inefficient or will not learn well will be automatically removed in favor of models that are more sample efficient. So this is hard-coded into the evolutionary framework. So this kind of makes sense. Cool. To wrap it up, so thanks again for coming to the open house. The high-level idea that we proposed is HD twin generator, which is a evolutionary framework. And the idea is that we want to learn hybrid digital twins given only user instructions and some data. And we highlighted that to do this automatically encounters an intractable optimization problem. And we introduced an evolutionary search technique where the LLM plays a crucial role of being a sort of search operator. And it also plays a role as an evaluator. And together, these two components help us better come up with better and more optimal hybrid digital twins. Empirically, we observed that the evolved twins exhibit enhanced generalization as well as improved sample efficiency. And the coolest part is probably the fact that it is modularly evolvable, which is a very important real world requirement. And there are many ways that the work can be extended. I think one of the more interesting ones is how do we most efficiently incorporate a human in the loop? So to maximize the amount of information that we can get from a human but limiting the amount of sort of work that they have to do. So that's a very interesting research question. And obviously the framework itself could be enhanced in many ways. So one obvious one is, for example, the modeling agent and the evaluation agent could have access to retrieval techniques where they can retrieve relevant texts or medical texts from a database. And this can likely enhance the performance. Cool. And just to wrap up, I want to say a big thank you to the Cambridge Center for AI and Medicine, as well as our sponsors, AstraZeneca and GSK, whose support have been pretty critical to getting this work done. Thank you.
So I think now onto our final slot for the day, which is AI for human empowerment. We have 3 really good talks upcoming. So Kasia, if you'd like to get us going.
Hi everyone, I'm Kasia. I just finished my first year of the PhD in the lab, and in this session I will present my work on informed meta-learning towards automated integration of knowledge from human interpretable representations. Let us begin with a little bit of a background motivating this work. One of the big challenges in deploying machine learning models in the real world is the scarcity of the data. When data is scarce, we must rely on the in-domain knowledge of experts that guide model design in order to encode this expert knowledge as the so-called inductive bias of a model. Inductive biases can be seen as the prior probabilities of different solutions within the hypothesis space of a model. The stronger the inductive bias, the fewer samples of data we need for the model to converge towards the optimal solution. A well-designed model is such that its hypothesis space is large enough to contain the ground truth solution, but at the same time, it exhibits strong preferences for solutions that closely align with the ground truth. And this is non-trivial. So let's take an example, the task of image classification. A convolutional neural network would be a really good choice for this kind of task, as its inductive biases help the model to learn spatial invariances. On the other hand, if we try to fit a linear regression model to this task, it would be a very poor choice because likely the true solution lies outside of the hypothesis space. In contrast, a generic neural network, while it does contain the true solution within its hypothesis space, its inductive biases are not very strong, and therefore we would require a lot more samples of data to recover the optimal solution. So how do we go about selecting the right inductive bias? Essentially, we can consider every conventional machine learning problem as being represented by 3 elements. We have the context data, which is also known as the training data. And in this work, we stick to the convention of using the word context data instead of training data, because that's how typically we refer to this data set in the meta-learning setup, which we will refer to later. And then we have also our target data, also known as the test data. So this is the data set, the held-out data set that we want to make our predictions on. And also we have an additional piece of knowledge about the learning task, which represents the knowledge of the practitioner or the in-domain expert that guides model design. So for instance, in the case of a simple one-dimensional regression, this knowledge could convey information about the expected shape of the fitted function, such as it should be monotonically increasing. Our goal is then to design a model that makes predictions on the target data given the context, that is the training samples, and the model should be such that it reflects the additional knowledge about the given learning task. Conventionally, this problem is solved in a very much manual way. So we start off with this knowledge representation, and then which is just typically conveyed in natural language. And then we have the machine learning practitioner interpreting this in-domain expert knowledge and translating it into a final model that encodes this knowledge as an inductive bias. This can be achieved by, for instance, adding some specialized loss functions, using special data augmentation techniques, or designing a custom model architecture. The final model is then obtained by training on the provided context data. And overall, this process is quite labor intensive, and its success relies on the extent of which the domain expert knowledge can be encoded into the machine learning model, which is, as I said, a non-trivial task. And then there's the alternative approach to the problem of inductive bias selection, which is to which is based on the idea of meta-learning. And it essentially enables us to automate the process of inductive bias selection by pre-training our model on a collection of related learning tasks. By training the model on this collection of related training tasks, the model learns an appropriate inductive bias itself, such that after observing a small sample of the training data for our task of interest, it can quickly be adapted to it without requiring a massive data set for training. However, the paradigm of meta-learning does not enable the human domain expert to take control over the inductive biases that are learned during meta-training. This meta-training process is quite, I would say, black box in nature, and it depends in a intractable way on the set of selected meta-training datasets. So in light of this, we want to find a new method of inductive bias selection that is A, automated, meaning that it requires minimal human engineering efforts, and B, it enables human interpretable control, such that the selected inductive biases are directly based on the in-domain expert knowledge represented in its native format, such as natural language. To address the problem, we propose a new model of automated and controllable inductive bias specification via knowledge conditioned meta-learning, or in short, informed meta-learning. So while the conventional meta-learning approach learns like a fixed prior over the hypothesis space of our model, instead we consider learning a knowledge conditioned prior that maps arbitrary representations of knowledge to knowledge conditioned priors. This learned mapping between the space of human interpretable knowledge representations and the hypothesis space of a model enables us to generalize. It would be good if this learned mapping could generalize to previously unseen representations of knowledge, such that given a new, previously unseen piece of information, it can adequately map it to a prior distribution over the hypothesis space, assigning higher probabilities to solutions that are in agreement with the information conveyed within the given representation of knowledge. So how do we go about learning this map? In order to do so, we must assume access to a collection of training tasks which are represented by, as previously, but now we have a big collection of these tasks, by context data, target data, and the representations of knowledge. We then assume that context and target data sets are generated according to an underlying function f, sampled from an unknown stochastic process, and then given such a sample function, the observable data is generated by introducing some unpredictable observational noise. And then for the knowledge representations, the knowledge pertaining to each task is represented in a human readable format, such as natural language, and then it contains truthful but often incomplete information about the underlying function of interest. So we assume that knowledge about a fixed function is generated according to a distribution which captures the variation of knowledge representations due to their semantic equivalence. This is because a single property of a sample function can be described by many semantically equivalent sentences in natural language. This variation also stems from the incompleteness of knowledge, because information expressed in a sample knowledge representation is often insufficient to unambiguously determine the values of the function across its entire domain. So for instance, if we say that a given function is linear, we are still missing the information about its slope and its bias terms. In a nutshell, the training of an informed meta-learner starts from gathering the collection of meta-training tasks. We then optimize the model to find the meta-parameters that maximize the likelihood of our target data given the context data and the additional knowledge about about the given learning task. This objective is then optimized against the entire distribution of the meta training tasks. After meta training is completed, at test time, we can make informed predictions by presenting the model with a small few-shot sample of the data, and if available, the additional expert knowledge. So in this example, if we say that the function should be increasing, the fitted function should be increasing, the prediction intervals should narrow down to the set of increasing functions only, which here is represented by the purple shaded area. But this is like just a visualization of what we would like to achieve with the process of informed meta learning. In our paper, we have a theorem which enables us to theoretically motivate our proposed approach. And the key insight of that theorem is that basically successful integration of knowledge into the machine learning model necessarily manifests itself in improved predictions and therefore improved data efficiency. We then go on to testing this claim, starting with some simple synthetic data experiments. We construct regression learning tasks by sampling ground truth functions from a family of sinusoidal functions whose shape is governed by 3 parameters, A, B, and C, corresponding to the slope, the frequency of oscillation, and the bias term. And then knowledge representations reveal the ground truth values of 1 or 2 of the ground truth parameters A, B, or C. So when no context data or extra knowledge is provided, which is here represented in gray, sample predictions exhibit a high variation. They represent the heterogeneous prior distribution that was learned during meta training. But after conditioning our model on the additional knowledge about the value of the parameters, we can see that the predictions adapt accordingly. For instance, if we specify the value of the frequency of the oscillations, all the sample predictions represent sinusoidal functions with the given frequency of oscillations, which is exactly what we would like to see. And then as we observe more and more data, our predictions adapt accordingly, and the more knowledge we have about the given learning task, the fewer data samples we need essentially to converge to the ground truth solution. By looking at the laws of the 2 types of predictions, the uninformed ones, which are here presented in purple, and the informed predictions presented here in green, we can immediately see that providing the model with additional expert knowledge about the learning task results in a significantly lower prediction error. And this validates that our informed meta learner has successfully learned to integrate knowledge into its predictions. In the paper, we also discussed the differences in uncertainty reduction given sample data and given knowledge representations. And while sample data conveys information about the expected value of the function, which is very local in nature, knowledge representations enable us to convey a much wider range of properties, which are more global in nature, such as, in this example, slope, bias, or oscillation frequency. But this synthetic example serves only to anchor the key ideas of informed meta learning. In a real-world application, we will be interested in cases where knowledge is represented in its native format, which is natural language. And of course, with the current development of large language models, there is nothing stopping us from testing this idea. In our paper, we look at 2 experiments with real-world data and knowledge represented as text. And one of them is an example of time series prediction, where we aim to predict the evolution of the temperature throughout the day, with knowledge represented as oracle weather forecast for the given day. And we can see that our model has learned to correctly interpret the information contained in these knowledge representations, and then translate it to appropriate priors, and then informed predictions which as a result narrow down the prediction intervals to their appropriate range. And then we have a second example in which we consider the problem of image classification, where the task is to predict the class of a bird, given a small few-shot sample of training images and additional knowledge about the characteristic features that pertain to a given bird class. And as expected, the predictions made with informed model having access to this additional information in form of the characteristic features of a given class of birds are significantly improved upon the pure data-driven predictions. So in summary, in this paper, we introduce a new perspective on inductive bias specification via informed meta-learning, which enables us automated and controllable specification of inductive biases based on human interpretable representations of knowledge. Learning the map between knowledge representations and the hypothesis space of the model establish a sort of communication bridge between the human interpretable space and the hypothesis space of the model. This enables a direct integration of in-domain expert knowledge into final predictions, which in turn leads to significant improvement in data efficiency. Thank you all, and I would encourage everyone to check out the full paper for more details. And I would also like to thank my sponsors, ED, for supporting this research.
So hi, everyone. I'm Hao Sun from the Vandeshar Lab. I'm a fourth-year PhD student, and I'm working on the intersection between inverse reinforcement learning and large language models. Today, I will be presenting our recent work using reinforcement learning to enhance the large language model prompting, fine-tuning, and inference time optimization. Here will be the content of my presentation today. I will first go through some basic concepts in reinforcement learning and inverse reinforcement learning, and then I will introduce our understanding of the large language models. And then I will talk about our recent research on the intersection between these two areas. And importantly, I will cover some topics on the techniques that makes ChatGPT good and the techniques that make the O1 model even better. And limited by the time today, I will mainly introduce two use cases or main cases of our research. The first one is offline inverse reinforcement learning for mathematical reasoning, and the second is using inverse reinforcement learning for alignment from demonstrations. So let's start from the concept of reinforcement learning. So in reinforcement learning, we have an agent interact with the environment. Here, the environment always have two components. They are the dynamics model and the reward model. In every time step, the action is executed in the environment, and the environment will also output and reward. In such a step, if our agent is learning from trial and error, the execution and evaluation of these actions would be quite expensive. So think about learning to drive or learning to prescribe some medicines to the patient. All of this will be like difficult to execute these actions in the real environment or to evaluate how well those actions are. So that's why we need to learning by imitating from the imitating the experts. And in reinforcement learning, we call this behavior cloning, which means we do supervised learning to the experts' decisions, such that we can learn good policies. It is worth to mention that large language model is a quite a special case. In this case, the large language models themselves are not only agents that interact with the environment, they are also the dynamics models. This is because in large language model generation, we generate tokens step by step, and after every step, we generate a token, and then we concate them with the existing token sequences. So in this process, the dynamics model is known and deterministic. It is concatenation between different tokens. And in this case, the only challenge for us is the unknown reward model. In practice, people always use human feedback to provide preferences into the fine-tuning for the fine-tuning of large language models. And in this type, this preference data could be very expensive. And that's why we need a reward model as a cheap proxy from the perspective of inverse IO. From the perspective of large language models, we know that large language model training has two important phases. The first is supervised fine-tuning, supervised learning or pre-training. And the second phase is post-training, inclusively the supervised fine-tuning and reinforced learning from human feedback. Out of these two phases, behavior cloning is quite important. And both the supervised learning in the pre-training phase and the supervised fine-tuning can be viewed as behavior cloning from the perspective of inverse IO. Also, the RLHF and all of these techniques are imitating natural languages. We also know from the literature that large language models can provide approximate knowledge because we are learning the huge database using relatively small, although they are large language models, we are using a relatively small number of parameters as compared to the knowledge we store in the large language model. So they can provide some approximate knowledge. They are good generators, but they are not expert for anything. We need reward models to optimize their performance in every task. So to better illustrate this, we can, for instance, let's consider some task. The large language model can be used to generate multiple responses or multiple solutions to this task. Out of those multiple solutions, they may not be all good or all bad. So we have the task performance distribution here, and the y-axis is a probability. So ideally, we hope we can get good performance, which means we hope we have distribution shifting toward the right-hand side of this x-axis. And in practice, we know that smart prompting can improve the task performance, or we can, if we have some good expert demonstration dataset, we can fine-tune our language model using supervised fine-tuning such that the output distribution can be shifted toward a better performance. Or from the inverse reinforcement learning perspective, if we can have a reward model here, we are able to filter out the bad responses and only keep the good ones. In this case, the output distribution will also be equivalently shift to the better areas in the task performance axis. And this reward modeling method can be combined with prompting or can be combined with supervised fine-tuning, such that the performance could be further improved. This is especially useful in the challenging tasks like mathematical reasoning, where language models themselves can sometimes, or in most cases, could not directly provide a good answer. And in this case, a reward model can be used to boost the performance. So to summarize, reward models provide the only way of doing inference time optimization. And that's why we need research on reward models. And here are some our research on the reward models. And they are all centered in the intersection between inverse IO and large language models. We study on both the inverse direction, which means we build reward models from data. Our research has focused on building reward models from binary data, on reasoning task, building reward models from preference-based data, and building reward models from demonstration or expert data. On the other hand, our research also focused on apply those reward models in the forward direction, which means how we use the reward models smartly to make large language model generation stronger. And in this forward direction, we have researched on a data-centric research study when are these reward models useful from a data-centric perspective. We have dense reward, and recently, sometimes we call it process supervised reward. That is essential for like reasoning tasks. And we also has a research combining search with this dense reward. So out of this research, some of them, including the zero-shot chain of thought, reinforcement learning from human feedback, and online reinforcement reward modeling, are essential techniques for ChatGPT. And the process reward and the reasoning or combining search with the dense reward are crucial techniques for the recent O1 model. Today, I will, limited by time, I will mainly talk about the inverse direction of building reward models from binary data and from demonstrations. So let's begin with the first use case. It's inverse reinforcement learning for prompting optimization in mathematical reasoning. So here's an example of how we interact with ChatGPT. So sometimes we directly ask the question and GPT can provide a correct answer, but we also know there are some smart or advanced prompting techniques can be used to further improve the performance if the GPT cannot give the correct answer at the very beginning. However, we also know empirically this prompting mechanism are query dependent, which means there is no prompting strategy that works for all different queries. So automatic prompt engineering is expensive, but they are useful. In practice, if we formulate this as a reinforcement problem, we can interact with a large language model to provide different prompting strategies to them and then collect feedback. This is doable from the perspective of IO, but would be super expensive given the fact that we have a huge vocabulary space to explore or interact with a large language model. So in order to get automatic prompting strategy, in our work, we introduce the method of learning from set demonstrations instead of learning how to prompt language models from scratch. So the difference is instead of directly interact with the environment using the approach of reinforcement learning, we propose to optimize those prompting strategies using offline inverse reinforcement learning, which means we first collect some expert demonstration dataset of how to prompt, and then we hope we can distill this knowledge from expert into the prompting agent. So we are standing on the shoulders of giants. In practice, how we collect this demonstration dataset, we highlight that this demonstration dataset exists in the literature as a byproduct of previous research. So in previous research, we have different prompts or prompting strategies proposed by previous researchers, and all of this research have benchmarked their proposed prompting strategy on open-sourced query answer dataset. And during benchmarking their prompting strategies, we collect different query prompt response pairs, and we know whether these responses are correct or not, because people always evaluate the accuracy of answering math questions in their experiments. And with this dataset, we actually have everything we need to build inverse reinforcement learning for prompting agents. Because with these tuples, we can use the query and prompt as input and try to optimize the reward model to predict whether this combination leads to a correct answer or not. So we can build effectively a reward model within 5 minutes in our case. And then we can apply this reward model to optimize our prompting strategy. Here are the performance of our method on math reasoning tasks. We can see it drastically improved reasoning performance, and it is worth to note we only need 5 minutes to train one reward model for prompting optimization. In the second case, I will introduce our recent work on using inverse reinforcement learning for alignment from demonstrations. In practice, people do fine-tuning or reinforcement learning from human feedback to improve the quality of language model generation. How it works begins from a single prompt or a batch of prompts, and then people ask the language model to answer these queries or give responses to this prompt, give multiple responses. And then we have annotators to annotate which response provided by the language model is better than the other. And then we can distill a predictive reward model from this preference-based annotation. And finally, we can optimize our language model with this learned predictive reward model. What is wrong with this previous approach? First, preference-based alignment is expensive because we need human annotators. And also we need some additional assumption like the predictive model to transfer the preference data into absolute scores in the predictive reward model. Also, because these multiple responses are generated by a single language model, they are always of similar quality, so the preference data annotation can be very noisy. lastly, there could be some privacy concerns in the annotation process. For instance, some of the responses are highly correlated with the input information, and if this input information includes some patient information, we cannot share this with annotators. In our work, we introduced to use inverse reinforcement learning to solve this alignment from demonstration task. For instance, this can be applied in the future, like prescribe medicine to a patient or sterilize an email generation using large language models. In the literature, people always use supervised fine-tuning to learn from demonstrations. But in our work, we are the first to apply inverse reinforcement learning to first distill a reward model using the techniques of inverse IO, and then apply this reward model into alignment of large language model. In our work, we highlight the supervised fine-tuning, which is a common practice in learning from demonstration, is actually distribution matching from the perspective of inverse IO, and it is using the forward KL, and this can explain their behavior of mask covering. On the other hand, if we are going to seek do mode seeking, we need more advanced inverse IO techniques and consider the reverse KL. And this requires smart reward modeling, which we introduced a method in our work. And here are some results of how this forward KL works. This is performance of supervised fine-tuning. As we mentioned before, our framework can be used to understand why supervised fine-tuning can be good at some of the cases. For instance, in the harmless, this is because in this harmless task, we only need mask covering behavior. And on the other hand, if we have multiple mode in the response distribution, we need more advanced method like the reverse KL or inverse IO reward modeling based method. And this can further improve the performance and outperform the demonstration behavior or demonstration quality. It is worth to highlight that inverse reinforcement learning provides the only way of outperforming human or expert demonstration. And thanks for your attention. Here are some references.
Thank you, Hao. I'm going to take over a little bit from Nabeel to introduce the final speaker of the day, who is Tim Schubert, who is not a PhD student in our lab, but he's an affiliated PhD student, MD PhD affiliated with our lab. And I'm excited about this project because it is the first time we are able to build something that I hope to be truly useful for many of our clinical collaborators who are very keen to engage with machine learning, and yet they are not able to speak Python. Thank you, Tim.
Thank you, Mihaela, for the introduction, and I'm really excited to be here and speak to you today. Thank you for coming to the open house. As Mihaela said, my name is Tim Schubert. I study medicine in the MD PhD track at Heidelberg University in Germany and have been involved with research projects with the Schaar lab for quite some time now. And with all the projects we had and all the discussions we had, what we always came back to was that issue that a lot of amazing tools and methodologies are being developed, particularly by the lab, but at the same time, there seems to be limited translation into actual clinical practice. And today I will present to you Climb, which is an AI-enabled partner for clinical predictive modeling, which we hope will actually bridge this divide. Of course, I present this on behalf of a team. First and foremost, Professor Mihaela van der Schaar and Evgeny Savelyev, and of course also Thomas Poplin and Vasilis Kosmoliaptis, who really contributed to this work. So first, I just want to mention again that prediction is really one of the pillars of individualized medicine. And I'll just highlight this with one example. In breast cancer therapy, there's a question of whether adjuvant treatment, so treatment after radiation therapy, for example, should be given or not. And this can be guided by risk prediction. This is actually a paper that has been published in 2021 by the lab. And they basically used patient registry data built a predictive model, and this predictive model was able to predict the survival benefit with therapy and without therapy, such that it actually gives you a good rationale for whether therapy will be helpful for a specific patient or not. We argue that clinician scientists should be the people who build these predictive models, and there are several reasons for that. Clinicians are the domain experts who can actually identify real-world clinical needs, i.e., what do I need in my daily clinical life, which kind of prediction would be meaningful. Clinician scientists, if they develop these models, will also be able to bridge the divide between model development and the real-world application, because they will actually build the models that they will use in clinical practice. But domain expertise is not just nice to have, it's actually crucial for several reasons. It is necessary for setting the agenda, of course, i.e. which predictive models should be built. But it's also really important for understanding the medical data that is being used to create these models. And it's important to be able to interpret the validity and the clinical relevance of predictions that are being made. Of course, you could say, well, you could just pair a clinician with a data scientist. However, it has been empirically shown that dual expert teams are costly, they're difficult to assemble, and they're also prone to insufficiencies due to misaligned goals. Our vision, therefore, is that we should have a cycle of clinical risk prediction, basically. So starting in the top left corner with patient care. Clinicians care for their patients, they generate data in the process, and this data would then be used to create a predictive model, ideally using state-of-the-art machine learning or other state-of-the-art techniques. These models should then be evaluated in prospective trials, implemented in clinical practice to then improve patient care again. And of course, the cycle can be actually circular and be completed time and again to continuously improve patient care to bring us closer to actual individualized medicine. Today, I will mostly focus on the part where we have medical data and a medical or predictive problem, and we want to build the model. Predictive modeling itself is hard, and maybe this is trivial, but currently substantial expertise is actually required to develop solid predictive models. Challenges include reproducibility, interpretability and explainability, trustworthiness, and also really important is the no free lunch theorem, which basically postulates that there will be no single method that is ideal for all kinds of prediction problems. That means there's a question of how should you choose the optimal data engineering steps, the optimal machine learning method, the optimal hyperparameters, etc. Now, this problem is not new, and there is one potential solution. Again, we have many diseases, many variables, various needs. Of course, you could do a brute force selection of ML methods and the design parameters, but this requires substantial expertise and is also prohibitively expensive if done by a human. This is why people came up with this idea of making machine learning do the crafting and the optimization process, something that we call automated machine learning, or short AutoML. Now, the Schaar lab has actually developed the first automated machine learning framework for clinical risk prediction, autoprognosis, and this has been applied to a variety of diseases, as you can see on the bottom right. However, there are some remaining roadblocks. Automated machine learning optimizes the model building process, but automated machine learning tools still require technical expertise, and they require coding skills. They lack intuitive interfaces. And crucially, and I think this is probably even the most important thing, they fail to address the data exploration and engineering phases, which, let's face it, are the most time-consuming in most projects like this. This is why we want to introduce CLIMB, the Clinical ML Building Partner. What CLIMB does is, we start with a clinician who has a problem, a goal, and a data set of real-world clinical data that hasn't necessarily been pre-processed. This can be fed into CLIMB, and CLIMB has a structured plan and guides the clinician scientist through the entire pipeline of predictive modeling. starting with data exploration, then data engineering, model building, and model exploitation. And for each of those phases, it has access to state-of-the-art tools. Together, the clinician scientist and Climb can create a predictive model, accompanying visualizations, and a summary report. Climb provides holistic support for all phases. It has an intuitive user interface with chat and dashboard. It follows data science best practices within a structured plan. It provides interpretable visualizations and explanations to the clinician, and this is, of course, interactive, so they can actually ask questions about anything that is unclear. In addition, the tool library itself is modular, as well as the LLM component, which means that it can be expanded or changed in the future. Climb can handle diverse problems already and flexibly adjusts to the clinician's requests. And of course, there are privacy measures in place to protect the clinical data that is being used. As you can see here, Climb already has access to a lot of tools, a lot of which have also been developed by the lab itself. And we will continue to extend this library of tools in the future. But for now, I just want to show you that this is not just a vision or an idea, this is actually real. And we'll show you that with a demonstration. So I'm very happy that Evgeny is here today as well and will be able to share these demonstrations with us. And I will not talk too much during the demonstrations, such that you can really take them in, but I will offer a few explanations to explain which part of the modeling process we're in.
Yeah, whenever you're ready, Tim.
Okay, let's start with the first one. So you will actually see a session where a transplant surgeon built a regression model. We start in the data exploration phase, and with exploratory data analysis, it's already been done. You can also see the correlogram, which basically shows the correlation between variables. And then it basically guides the user through the plan, which you can see on the right-hand side. The next step, it will ask the user basically to create descriptive statistics, and that will happen in just a second.
Here are just the results of the EDA being reviewed, and I think briefly we will highlight that there's a correlogram and an explanation. So yeah, the next step is indeed EDA, as Tim has said.
Brilliant, thank you. And basically, as you can see, the tool has this chat component on the left side and the plan on the right side. And the right side is actually the dashboard that has different tabs. Right now we see the working directory. And as soon as the descriptive statistics have been generated, you will also see that plots are being generated for all of the different variables. Now, actually, what is really cool about this is that Climb tries to infer which of the features are the most interesting to the user. And it actually will show the plots for these features specifically within the chat. And any other plots will be available from the right-hand panel.
Yeah, and you can see the highlighted plots on the left in the chat panel, and all the plots for all the different variables on the right. I think next one, Tim.
Brilliant. Yeah, let's move on to the next phase. So this was data exploration. Now we're moving on to one of the parts of the data engineering phase, where missing values are being handled. In this case, the clinician wanted something quite specific, and you will be able to see how Climb actually adjusts to this request flexibly and can handle these very custom rules. So as you can see, Climb will generate code in this case to handle that request. And of course, now that changes are being made to the data, it's really important that this is interpretable and that the clinician scientist will understand which kind of changes have been made. And we'll see that in just a moment, that this is being enabled also by the dashboard.
Yep. So you can see essentially how dynamically your data set has changed. So here in green, for example, you would see where imputation has been performed on user request. It'll also show things like which rows have been dropped or columns have been dropped.
Brilliant, thank you. Then we move on to the third stage, which is a combination of the model building stage and then the model exploitation stage. So at first, we see that Climb will use the auto-prognosis tool to perform a regression study for the clinician. So you can see auto-prognosis being run here. And again, this is the automated machine learning package developed by the Schaar lab for clinical risk prediction. Now, some of these metrics may not be easily understood by the average clinician scientist, which is why explanations of any more technical metrics are offered automatically by the tool. And after this, we will actually do a little step, at least one part of the model exploitation part, where we run a SHAP explainer tool. This is also part of the plan. And this, of course, gives you insights into feature importance. So again, it will run the tool and it will generate both a textual output, but also visualizations. Yes, so you can see the B-swarm plots here. And overall, this was really just a very short snippet as a demonstrator to show you. But there are many more tools under the hood in Climb. There are many more steps that it can perform and that it will guide the user through. So I think at this stage, let us go back to the PowerPoint. And for the last bit of the presentation, I just want to briefly share our vision for this tool. We think of Climb as a core technology that can be expanded in the future with more modalities, more tools, and more problem scenarios. So we're thinking imaging, we're thinking other tools that are relevant to interpretability, for example, other data-centric tools, etc. We believe that Climb will truly democratize predictive modeling and actually enable progress toward reality-centric solutions with a tangible positive impact on healthcare. A huge thank you to our main sponsor, Microsoft, for supporting this research. And the paper, the preprint is out now. I've also included the QR code here for you, and I really encourage you to read that paper. Thank you so much.
Thank you very much. Otherwise, we are tremendously grateful for your presence, and we are very much thanking you for all the support, and to the collaborators for all the wonderful collaborations. And all of this will be online relatively soon. Andreas will process it and post it, and it will be sent to you such that you can take a look. And we look forward to hearing from you and to continuing to collaborate with you all. Thanks a lot. Nabeel, I don't know whether you want to say a few words as well.
No, I think more generally to all the sponsors, I think from all the students, I think we can definitely say a big thanks to all of the sponsors and collaborators. It really makes our job as researchers much easier, and thank you for all the support.
Huge thanks.